Okay, so we're talking about operations with matrices and specifically addition and subtraction. It's very straightforward, so we can take a look at an example. So matrices can only add or subtract when they have the same dimension. So both of these matrices are 2 by 3 matrices because they have 2 rows and 3 columns. Remember, row comes before column, RC. And so because these matrices have the same dimension, we are allowed to add it. And all we do is add simply the corresponding elements. So 3 plus 0 is 3, so this will be 3. 6 plus 5 is 11, so that's the next one. 3, 11, and so on. 3, 11, 4 minus 2 is 2, and 2, 9, negative 2. Okay, so that's matrix addition. Super easy. Okay, and it'll always give us a matrix with the same dimensions. Same for subtraction. No problems there. We're also allowed to multiply matrices. Or first, let me maybe talk about what happens when the dimension is not the same. Let's say we were adding like 2, 1, 1, 3 plus 1, 2. This is illegal because the dimensions are not the same, right? So you can just write illegal. Or maybe don't write that. That's like politically sensitive nowadays, so it's not right illegal. Maybe undefined. Okay, let's do multiplication by a scalar. You guys know what a scalar is, right? All of our physics friends.
It's the thing you use to climb a wall.
No. A scalar is just a number, right? A number as opposed to a vector or a matrix, right? So for instance, if I were doing, 5 times this matrix, negative 2, 1, 4, 0. If I'm multiplying by a number, then I just multiply every single element by that number. So it would be negative 10, 5, 20, 0.
So it's just a coefficient?
Sure, yeah. Scalar is more mathematical.
Coefficient's not mathematical now?
I mean, it becomes a coefficient when it's multiplied, but I'm multiplying by a scalar, a number. Okay, so this is very straightforward, and it follows all the normal properties, like this obeys the commutative property, the associative property, distributive property, all of those things. So very easy. Any questions? Okay, then let's do the hard part, and that's matrix multiplication.
I thought you said it's easy.
Well, I think it's easy, but it's harder than this.
Oh, okay.
Matrix multiplication?
Oh, the movie? It's been a while. Okay, so matrix multiplication. Perhaps I will bring this to the next slide. How do I do that? I select it. Wait, no. Select it and then drag it. Hello? Oh, screw it. Matrix multiplication. Okay, so you're allowed to multiply matrices when they have a specific relationship in terms of their dimensions. You can only multiply an m by n matrix with the m by p matrix. Okay? So you can only multiply them when the first factor has the same number of columns as the number of rows in the second factor. Okay? So n has to match the n on the second side. So for example, you can multiply a 1 by 3 matrix by a 3 by 2 matrix. So this would be a legal product. This, on the other hand, a 1 by 3 times a 2 by 3, that would be illegal because these numbers don't match. Okay? And so a m by n matrix times a m by p matrix will yield a m by p matrix. Okay, so a 1 by 3 times a 3 by 2 will give us a 1 by 2. And this would not give us anything, right? That's illegal. Okay, so let's do an example, and I'll explain what the procedure is for multiplying two matrices. Let's say we had, we do easier one. 1, 3, -1, 0, 4, 2. So what dimension is that?
3 by 2 by 3 by 2.
3 by 2, very good. Okay, let's say we're going to multiply that by 2, 0, -3, 1, 1, 4. Okay, that's a 2 by 3 matrix, right? So this multiplication is legal because the second number here is the same as the first number here. Okay, and it will give us a 3 by 3 matrix. Okay, so how does this multiplication work? Okay, we can draw the matrix first. We know it's 3 by 3. Okay, so for this first element here, let me use a color. For this first element here, what we do is we take the first row of the first matrix and multiply it by the first column of the second matrix. So the result is 2 plus 3. And I multiplied those, the row by the column by multiplying each individual element by the other one. So it becomes 1 times 2 plus 3 times 1. So that's how I got 2 plus 3. Okay?
You don't need to do 3 times 2.
You're not supposed to. You take the first element multiplied by the first element here, and the second element multiplied by the second element. And then you add them together. Okay? So it becomes 2 plus 3. And then the next one, this element here, what I do is I take the first row and now the second column. Okay? Why is that? That's because this is the position first row, second column, right? So I take the first row of the first matrix and the second column of the second matrix. Okay? And that's going to give me 0 plus 3. All right? It's 1 times 2 plus 3 times 1. And then the second one, 0 plus 3, that comes from 1 times 0 plus 3 times 1. So I have to go piecewise in that L pattern.
Distributing everything.
It's not distributing.
At the end of this unit, we should watch the matrix.
We don't have time for that. Okay, and then the next one, it's going to be the first row times the third column. Okay, so that would be -3 plus 12. So we get 9. Okay, so my final answer, if I keep doing it for all 9 entries, I'm going to get 5, 3, 9. And then once I get to the second row, I need to do the first row times the second column. Okay, so that's going to give me -2. This will be 0. And then 3. And 10. 2. -4.
First row, second column.
Okay. Let me draw new colors here. Okay, once I get to the second row, it's going to be the second row times the first column. That becomes -2 plus 0, which is -2.
Can you give us that example problem?
What? This is the example problem.
Is the final box your,
Like
Huh?
first.
Yeah.
is the final box your answer?
Yes. This is my answer.
Like for us, it's like
Okay? It's -3 plus 12. Okay. So you have to do this sequential multiplication in that L pattern. Okay? It's always the row of the first one times the column of the second one, going in this order. Okay? And now you can see why these dimensions had to match. Because if these both weren't 2s, then we wouldn't have enough enough entries to match in that way of adding. Okay. Let me show you guys a different way of writing it that I saw on Reddit that I thought would be helpful.
Reddit, Mr. Nye?
I mean, I don't know what you mean by on Reddit. I use it as a resource sometimes. Okay. Anybody need to see the slide longer?
How much karma do you have?
I don't do anything on it. So. Okay. Yes. I can answer this afterwards. Okay. A different way of writing it that might be more intuitive is by placing the first factor on the left side and then writing the second factor on top, such that my final answer is somewhere here. This would be my final answer where the x would be, except I write the second factor now on top of it. Okay. So now the idea is that to find this entry here, I find the corresponding row that lines up with it and the column that lines up with it, and then I multiply those entries in order. So it'll be 1 times 2 plus 3 times 1, which is 5. That is somewhat more helpful. And then the second one would be 1 times 3 plus 0. Sorry. It will be this row times this column. So it will be 1 times 0 plus 3 times 1, which gives me 3. Yeah?
How did you get 5 again? Can you explain that real quick?
It's 1 times 2 plus 3 times 1.
1 times 2 plus 3 plus
I take, if I want to multiply this row by this column, I take the first element of each and multiply them by each other, and then I add the second element multiplied by each other. So it's 1 times 2 plus 3 times 1. You multiply these, and then you multiply these, and then you add them.
Okay, got you. Thank you.
Okay? And then, for the second one, I multiply these and add it with this product. So it's 1 times 0 plus 3 times 1, which is 3. Okay, and you can see that as I go down the line, right, my next entry is going to be 1 times negative 3 plus 3 times 4, which is 9, right? So I get the same thing as before. I think that's right. Yeah. Okay, so that would be my answer. Okay. Any questions? So something that's very important is that matrix multiplication is not commutative. Right? You guys, it's not commutative. You guys remember what commutative means, right? From pre-algebra?
Pre-algebra?
Yep, pre-algebra. Commutative property is AB equals BA, right? But for matrices, this is not true. For matrices, the commutative property does not hold. So let's say we flip the order of these two matrices. Let's say we try to multiply the second one and put that as the first factor. So let's say we're doing 2 0, negative 3, 1 1 4 times now 1 3 negative 1 0 4 2. Okay, you can very clearly see that the product is going to be different when I switch the order, right? Because now the product's the 2 by 2 matrix, right? Why is that? That's because I'm multiplying a 2 by 3 matrix now by a 3 by 2 matrix. So this product is still legal because, these match, but my result is going to be a 2 by 2 matrix and not a 3 by 2 matrix, not a 3 by 3 matrix. Okay? So I can multiply them once again. So this entry here is going to be 2 plus 0 plus negative 12. Okay? Which is going to give me negative 10, right? And then the next the next entry is going to be 6 plus 0 plus negative 6, which is 0, right? Next one is going to be 1 plus negative 1 plus 16. And then the next one is 3 plus 0 plus 8, which is 11. And so that's my answer. It's totally different, right? And that's because matrix multiplication is not commutative. Right? Sometimes it's not even going to be legal. You might have like a 3 by 4 matrix times a 4 by 2 matrix, and that's totally legal, right? What's the dimension going to be? 3 by 2. The 4's kind of cancel. All right, but what if I switch the order? What if it was that same 4 by 2 matrix times a 3 by 4 matrix? Now it's illegal because these numbers don't match. So switching the order sometimes makes it not even possible. Got it?
Yes, sir.
All right.
No practice?
You can do the practice yourself on the classwork, but let me talk about what the identity matrix is. Are we all good with this slide? Yes. Okay, last thing we need to talk about, and we're done. And that is the identity matrix. The identity matrix is simply the matrix that satisfies this property, which is A times I equals A, or I times A equals A. In other words, when you multiply any matrix by the identity matrix, it will give you the same exact matrix. Okay? And what is the identity matrix? It's that matrix where every entry is 0 except the diagonals, which are 1. So for example, the 5 by 5 identity matrix is just going to look like 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0 0 0 0 1. Okay? So all the diagonals are 1 and everything else is 0. I'll show you how this actually multiplies. Okay? Let's say we were asked to find this product, maybe like 1 4 3 2 0 negative 5. Okay, this is a 3 by 2 matrix. Sorry, 2 by 3 matrix. Right? And so, if I were to multiply it by the 3 by 3 identity matrix, okay, identity matrix is always square. You can confirm that by some basic logic. So if I were to multiply this by the 3 by 3 identity matrix, then I would get the same exact matrix as the product. Okay? You can confirm this, all right? So if I were to, calculate the first entry, I would multiply 1 times 1 plus 4 times 0 plus 3 times 0, which just gives me 1, right? So 1 is going to be the first thing. And then the second product is the product of the first row and second column, right? But what is that going to be? That's going to be 1 times 0 plus 4 times 1 plus 3 times 0, right? 1 times 0 plus 4 times 1 plus 3 times 0. But the zeros just make the 1 and 3 cancel out. So that just gives me 4. Okay. And then I can keep going for the third entry. That's 143 times 0 0 1. But that's just 3 because the zeros make the 1 and 4 disappear. All right? And you can keep going and you're just going to get the same exact entries. So that's why the identity matrix causes the matrix to just be the same when you multiply them. Any questions?